I'm going to jump right into it then. So before doing that, I just want to point out that the work that I am going to be presenting today is part of a larger project titled Evolution of Crustal Paleofluid Flow Systems through the UA and other collaborators from across the Southwest. And a lot of that has been supported by various funding agencies, but I want to point out that my work in particular is partly supported by the Courtright Scholarship through AGS, and I greatly appreciate that kind of thing exists for students like me and others that are recipients in the past and in the future. So, a lot of us in this room and probably in southern Arizona are probably used to ore deposits that are probably sound like things like porphyry copper deposits or gold lode deposits. And it's just something that's familiar given the region we're in down here. But today's focus is going to be looking at ore deposits that we can find in sedimentary basins, where things can become pretty complicated pretty quickly, given that there's all sorts of factors that influence a basin and its evolution. In this sort of time diagram I'm showing here on the right, and specifically for the Paradox Basin, we can see all sorts of geologic events that have occurred throughout its history of 300 million plus years. There's things like varying rates of deposition that we see here on the left. There's potential for salt movement or halokinesis throughout its history. There's also intrusions of various magmatic phases in that time period as well, and lots of other tectonic events that can influence the geologic history of the region. But on top of that, there's also a lot of different fluid events or fluid movement events throughout the basin, which can result in some pretty interesting elemental redistributions, as shown here in the middle, and results in accumulations of things like uranium and copper, which end up being the focus of this talk today. In addition to that, there's a lot of other fluids, things like hydrocarbons, basinal fluids, and things that have resulted in all sorts of alteration, such as bleaching, and again, ore deposition. But since this figure was put together, maybe a decade ago, there's been a lot of different changes in our understanding of the history of the basin with respect to the timing of ore formation and the geochemistry of ore formation. So today I'm going to be trying to convince you of some of the observations and interpretations that I have made over the last several years pertaining to those things. So jumping into the Paradox Basin, we are at the Four Corners region, roughly. So we've got Utah, Arizona, New Mexico, and Colorado. We've got that border that the basin is straddling. It's a late Paleozoic foreland basin. It's got considerable amounts of salt movement that has resulted in these gray salt walls that we see here in the northern part of the basin. There's extensive bleaching associated with those, shown in yellow, and of course the different magmatic systems that we see, such as in the La Salle Mountains, the Abajos, and others shown in red. Now there's considerable overlap of those things, both in space and potentially in time as well. And again, that's resulted in some pretty interesting ore deposits that we find throughout the region, such as the uranium and vanadium deposits, shown with these polygons in purple and in blue. Those in purple are hosted in Triassic rocks, and those in blue are hosted in Jurassic rocks, and is the main focus of one part of this talk today. In addition to that, there are copper deposits shown with these green diamonds as well, and just adds another layer of complexity to these systems. So in order to actually study these things, I've done so by spending quite a bit of time in the field doing things like mapping and sampling that I'm able to then use to bring back and supplement with various analytical tools that I have at my use at the University of Arizona here, things like a scanning electron microscope, microprobe, and uranium-lead geochronology assisted with the laser and mass spectrometer system we have. But to actually compare these things, it's important to do so in the first place. But to compare them, we look at shared characteristics, and then actually, as it turns out, within these different deposit types, there's an abundance of carbonate minerals associated with the mineralization that serves as a basis to compare and contrast these things. So I'm going to jump right into the uranium system to begin with, particularly those Jurassic-hosted deposits that I showed earlier with those blue polygons. And those are hosted in the Jurassic-Morrison Formation. The outline of the basin is shown in that yellow polygon there. There's an abundance of outcrops, mostly in the Four Corners states, shown with the blue. And then as you can see, overlaid on top of that with all these pink diamonds, there's numerous amounts of uranium and vanadium deposits hosted within those rocks, stretching all the way south in northwestern New Mexico, up northwards into the border region, the southern border region between Utah and Colorado. Now these are regionally associated with fluvial-dominated rocks, in particular the salt wash member of the Jurassic-Morrison Formation, which ends up being the main host rock in the northern part of the Morrison Basin's outline there. This is the next polygon we're going to jump into. So remember that square, or that rectangle. That's what we're looking at here on the right, where we can see that, again, we have the Utah-Colorado border running down the middle of that. There's an outline of the major districts of interest here. The Uravan mineral trend is that nice arcuate trend running roughly north-south. And then orthogonal to that is the LaSalle trend, which is a main focus of the mapping that I've done out here. And then overlaid onto that, we can see contours of the production of uranium from these districts. And we can see that there's potentially an interpretation to be made that there's some sort of drainage network here that's supplying potentially fluid pathways and other physical settings for uranium deposition in the subsurface following the formation of these sandstones. Just real quick, I'm going to walk you down in scale each time here, but just as a scale analog, again, we have the Uravan mineral trend in the LaSalle channel, as shown here on the left. And then comparing that to a major fluvial megafan here that we see draining the Himalayas here on the right. And we can see that, yes, once again, there is a potentially relationship between sort of these major fluvial drainages and mineralization. At a more local scale, though, these uranium deposits are mostly hosted in channel fill sandstones that are bound both above and below by mudstones that represent sort of these floodplain deposits that were once present during the late Jurassic. So jumping down in scale again, we're going to go into this red rectangle here where we have the LaSalle mineral trend. Again, this is a fairly narrow trend that's orthogonal to the main Uravan trend that's produced an abundance of uranium over the last century. But this area actually turns out to be a pretty good representation of the different features that we see in the Paradox Basin. For example, the laccolithic Oligocene intrusions known as the LaSalle Mountains. There's the Paradox Valley salt wall that represents sort of these major northwest southeast trending salt walls found in the basin. And then, of course, the uranium deposits that we see spanning all the way from the west in areas such as the LaSalle mine to the east into the Sal Creek Canyon, where we have an abundance more of naturally exposed deposits at the surface. Jumping down once more, I'll be taking you into this rectangle here on the bottom left, where we have a chance to look at some of the sort of legacy drill hole patterns that were produced over the last half century plus, where we can see that the mineralized areas shown with these yellow circles actually form this pretty neat mineral trend where we can start to make out sort of these channel meanders and potentially tributaries and even distributaries that again exemplifies that relationship between subsurface fluid pathways produced by ancient rivers and the mineralization that is associated with them. Sorry. In that white box there is an area that had some relatively recent drilling in 2019, where I'd had a chance to do some pretty detailed logging of core there. And the distribution of those holes is shown here in the middle, where it was used to target new areas to start digging around and looking for more ore. But those holes that I logged were 1 through 20, and they're represented with these red triangles there. And again, we can make out sort of that east-west trend of mineralization based on the presence of these mineralized holes shown with these black closed circles there. So stepping again down in scale, I've provided a photo example of some of the cores and the rocks that are associated with the mineralization here. And as it turns out, in these fluvial rocks, they're mostly dominated by these pink sandstones and red mudstones. But as it turns out, some of them have been partly altered to now be these white sandstones and green mudstones, which is more of a mineralogical change rather than chemical change. And that's best exemplified by looking at sort of the whole rock analyses that I acquired from a local whole rock geochemistry company. But as you can see, that the iron here is relatively conserved, and rather than a change in sort of the major bulk rock chemical assemblage, it's instead, the changes here are associated with mineralogical changes, such as the addition of quartz overgrowths, which I've shown in my core logging here with this blue line, the presence of carbonates, and other things. The last thing I'll point out is that there's a close association with the white rocks, or altered rocks in this case, and the black or mineralized mudstones or sandstones that we find within the LaSalle area. In order to actually compare those observations that I made in outcrop, or to things that you can find in outcrop, I went out into LaSalle Creek Canyon, where there's exposures, or excellent exposures of these spatial distribution of these alteration features at the Morningstar mine, shown in that red square there. So taking you there and comparing with what I already showed you, we have an outcrop map here at a roughly 1 to 500 scale map, where we can compare some of those similar lithologic features, such as the white sandstones shown in the outcrop there, the green mudstones shown in a small outcrop in the upper left there, and then of course the mineralized body of rock here, where that turns out to be in the gray zone there, representing the ore body. And once again, given the trend of this ore, we can get a sense that these were once, again, Paleo River channels that were trending roughly, in this case, east-southeast. Now within that ore body, there's actually an abundance of other features that we can map out. In this this second map here, showing some of those features that I briefly mentioned earlier, we can see that within the ore body, or outside of the ore body, there's a little bit of carbonate cement represented by these vertical orange lines. But once you step into the ore body itself, you sort of lose that, and it's no longer present except for in minute amounts in some of these smaller outcrops shown here in the middle and over in the southeast corner of this map. There's an inverse relationship to that with the quartz cements that we find in these bodies of rock, shown with this hatch pattern here. Outside of the ore body, we find very little silica cements in there, and with these crosshatch patterns within the ore body itself, there's an abundance of euhedral quartz added into the rock, and that's best shown with these thin section images here. So in the top, we have an image where you mostly just see detrital quartz grains. And then once you step inside the ore body, with this image here at the bottom. We see that detrital quartz grains again, but in this case it's overgrown with abundant authigenic quartz that's actually pretty euhedral in nature. The last map I'll be showing today is focusing on some other cements that we find in these rocks, namely the Ferroan dolomites that are represented with these brown open circles. And again, these things are mostly present outside of the ore body, and once you step in, it's only minimal that they're present. Instead of sort of Ferroan dolomites that we see as these spherical cements, we have things that are similar in shape, but are different in their mineralogy. So those black circles represent very similar shaped cements or concretions that are only present within the ore body and look like such. So outside of it, we see these Ferroan dolomite spheres or concretions that weather to this brownish hue, given the high iron content in them. And then inside the ore body, we have similar shaped features, but they're black, given the nature of the minerals within them, things like uraninite and monazite and coffinite, things like that. So just to summarize sort of the major spatial distribution features that we're seeing in and around these ore bodies. So the bleaching or white rocks in this case are found in many types of sandstones and mudstones as well. But within those, we see very little addition of authigenic silica. And instead, we have an abundance of carbonate cements and concretions, which range from things like calcite to Ferroan dolomite. And then once you're within the ore body, you're mostly within channel fill sandstones, where there's an abundance of, or significant development of quartz. There's very little carbonates within them. And then the concretionary cements that we see are mostly made up of uranium and vanadium oxides and hydroxides. Now, stepping further into detail with these uranium ore deposits, I've put up an X-ray map here on the right-hand side, where we can see sort of the different distribution of elements like iron, calcium, and uranium. And with knowledge of the mineralogy there, we can sort of make out the different paragenetic relationships or timing relationships between the different minerals that we see. So in black, I've labeled things like the detrital quartz grains. In the brighter blue here, in the middle, would be calcite. And then overgrowing that calcite, in this duller blue color, are the Ferroan dolomites that we see. Now, if you look closely, you can tell that it's the calcites that are intimately associated with these reds and greens, the reds being uranium mineral known as coffinite, and then the greens being pyrite. So with that knowledge, we can say that there's an intimate relationship between the calcite that's grown here and the uranium minerals. So we can then use those carbonates, or those calcites, to infer some things about the mineralization, such as their timing, as well as their geochemistry required to actually form these things. So with a new technique developed here at the University of Arizona, following techniques that have sort of slowly become more common throughout the country, we've been able to actually directly date the calcites that are associated with the uranium here. We do that by running a laser over these calcites and collecting various ratios of uranium and lead, and then plotting that on a Terra-Wasserberg diagram, such as the ones shown here on the right. So on the left, we have examples of the calcites that we were ablating with the laser, and those different shades represent either the uranium-lead ratio, as shown in the bottom left, or the total concentration of uranium, as shown in the upper left. So with that, we're able to produce ages that are roughly early Cretaceous in age, which is only within about 15 to 20 million years of deposition of the original rocks. So we can say that these things happened pretty early on in the rock's history, prior to some other inferences that have been made about the timing of these things by previous authors. So looking at sort of the other geochronology that's been produced from this region, where we can see potassium-argon ages and argon-argon ages of the major fault movements, mostly in the Eocene. There are other oxide development in the Pliocene here, and then other uranium mineralization ages that range from Triassic to sort of roughly Cenozoic. We can see that with these new ages, as shown with this gray bar here, they roughly overlap, but aren't entirely consistent with some of the previous direct dating of uranium mineralization, and in fact predate some of the other major events that have gone on in the Paradox Basin, such as that fault movement I mentioned earlier that's been dated with the potassium-argon fault gouge dating. So we're now done with the uranium system in the Paradox Basin region, and moving on to the Paradox Basin copper system, where we can start to look at things that are concentrating different kind of metals, in this case copper, and in some cases silver. So we're now in the northern part of the basin. There's our location map here on the right, so that red square is showing the northern part where we have an abundance of these major salt walls. And these deposits are shown in the green diamonds once again, and we can see that there's a pretty close association with things like those salt walls. There's an abundance of bleaching that they're associated with as well. And there's, in some cases, overlap in space with different kinds of organic matter, which includes things like oil and gas, as well as fossilized flora, as shown with the sort of brown polygons there. In addition to that, these deposits are intimately associated with the faults, both those that run northwest, southeast, along the major trend of the Paradox Basin, and those that run sort of roughly orthogonal to that, known as the transverse fault system there. And we see that at both the Lisbon Valley copper mine that runs northwest-southeast, where there's probably the largest accumulation of copper within the Paradox Basin, and at the Cashin copper-silver mine as well, where it's a little bit hard to see, but we can tell with this stereo net here that things are running, that a lot of the veins associated with the copper are running roughly northeast, southwest, perpendicular to those major trends. So I'm going to take you later on into the world of the Cashin copper-silver deposit. So remember where this is for just a moment while I give you examples of what these ores actually look like. So within the Paradox Basin, there's a lot of disseminated copper within these ore bodies that end up weathering to things like malachite and azurite, as shown up here in these upper two examples. There's also an abundance of breccias right along these major faults associated with the ore deposits as well. And those things are filled with, are cemented by barite and chalcocite, as well as some calcite, as shown here in the bottom middle. And then finally, there's an abundance of veins that mostly trend either with or orthogonal to the major mineral controlling fault here. So again, we've got chalcocite veins in the upper right, and calcite plus sulfide-bearing veins in the bottom right. And if you can note, these are all named for the different deposits that were studied in the Paradox Basin, that were visited, and it just goes to show sort of the consistency with these features that we see throughout the region, rather than these things being one-offs. So going back into the Cashin copper-silver mine, right here, running roughly northeast-southwest, is the Cashin fault. That is the main ore-controlling fault here, and it cuts across mostly Mesozoic rocks ranging from Triassic in age all the way up to late Jurassic at the tops of these canyon walls. Within that is the Jurassic Kayenta Formation, shown in these creams and reds, which indicates sort of the bleaching of these originally red bed rocks. And a lot of that work is based on mapping that Tim McIntyre had previously done while studying this ore deposit. But in more detail, I was able to describe some of the other alteration features associated with the bleaching and mineralization as well. So zooming in a little bit, we can start to see some of those features, and we can start to compare and contrast the geologic features between here and the uranium mine that I showed earlier. So along those bleaching boundaries, shown here with these sort of odd-shaped red polygons, there's an abundance, again, of these sort of concretionary cement features that are hugging that redox boundary there. And again, those are made up of carbonate minerals. There's an abundance of copper sulfide concretions that are right along the fault, unsurprisingly. There's also wholesale addition of pyrite and other copper sulfides, as shown with these orange blobs as well. And then there's odd pyrite nodules that are shown with these sort of large circular patterns in various positions throughout the bleached rock there. And just to give you a visual sense of what these things look like, so this is what the rocks look like, having previously been white and had abundance of copper and iron added to them. They end up with these dark hues with a little bit of those minty greens associated with the copper weathering there. Those carbonate concretions, again, have weathered to these sort of brown colors, but again, they're mostly hugging that boundary between red and white rock. And then lastly, the carbonate nodules that are found throughout various parts of the bleached Kayenta here. So in addition to those sort of cement features, there's also an abundance of veins in these systems, as I showed with those images before. So it's a little bit difficult to see, but right in the core of this ore body here, at least where it's exposed, there's an abundance of those green and orange veins, which represent calcite veins that contain copper sulfides, and then just copper sulfide veins alone in there. As you move away from that main ore controlling fault, either off laterally or up structurally, up section, we note that those veins are mostly red, which represents iron sulfides as opposed to iron copper sulfides. So just real quick, here are examples again of what these things look like. So we have these former copper sulfide veins that are bleeding these sort of malachite colors into the wall rock. There's also some subtle calcite veins in there that are running parallel to those. And then as you move up and away from the main part of the ore body, the veins end up being more pyritic in nature, and there's an absence of major copper within them. So again, back to the theme of carbonates. I just want to point out what those relationships look like between the minerals like chalcopyrite and bornite and other things with these carbonate group minerals. So up here we have a beautiful photo of some chalcopyrite intergrown with the calcite, and then from the Cashin mine, there's bornite intergrown with dolomites from the area. So again, we're using that same geochronology tool where we're dating a whole bunch of these things from throughout the Paradox Basin. And the calcites produce a bunch of ages that are either mid or late Miocene. And those are exemplified again with these Terra Wasserbergs here. I've only shown 4 of them, but there's a whole lot more. And then again, in the context of the Paradox Basin, it actually turns out that a lot of the previous geochronology related to the copper mineralization here puts the ages much earlier than these new numbers that I'm putting on here. So there's rhenium osmium that ranges from sort of mid-Cretaceous up through the Eocene, and there's major salt-related faulting going on in the Eocene as well. So it turns out to be pretty enigmatic that we have things mostly in the mid to late Miocene here, as shown with this gray bar on the right. Again, just to give you a sense of sort of the ground we've covered and the spatial distribution that's consistent over that area, I put a map up here on the right, which shows in these blue dots all the areas that we've been able to do this new geochronology with. again, these things from across the basin, and gives you a sense for the spatial distribution. And then in the bottom left, we have a temporal distribution of these ages, with a major peak in this histogram between roughly 10 MA and maybe 15 MA. So still trying to figure out how to interpret these things, but two possible hypotheses is that the faults are responding to sort of these far-field stress that's occurring as the basin and range region is developing, again in the Miocene, or it could represent early stages of exhumation of the basin and even the Colorado Plateau that have not been previously recognized by other geologists and geochronologists. So now that I'm done with all the geology and basic observational work, I want to get us into sort of the nitty-gritty of what the carbonates mean in the context of ore formation here, given that they're so sensitive to different kinds of chemical and physical parameters that influence their growth, and the distinctive geochemistries that they have, which could reflect sort of the fluids that they were forming from. So these images will pop up again shortly, but it just, again, goes to show sort of the complexity that carbonates present, given that they're intergrown with some of these copper minerals, as shown here in the upper part, and then there's complex oscillatory zoning within them. So the way we actually study these things and use to our advantage is by looking at different geochemical features within these carbonate minerals, looking at the trace elements, which again can reflect the pore water chemistry. We can look at their stable isotopes, namely the oxygen, to give us a sense of what the formation waters might have looked like. And something I've already touched on already is looking at the ratios of uranium and lead to give us a sense of the absolute timing of the formation of both the carbonates and the other minerals that they are formed with. So again, looking at the uranium first, and just looking at sort of the major cations that define their composition. So again, we've got this photo in the upper right that shows the relationship between the calcite and the uranium minerals. That's then later overgrown by those furrowed dolomites. So the calcites plot on this ternary diagram up in the calcite corner, of course, with magnesite or a magnesium-rich end member on one end and siderite or the iron-rich member of carbonate on the other end. So the uranium-related carbonates plot in the upper portion here, which I've expanded a little bit over in this corner. And then the parts of this ore body that don't contain uranium minerals but do contain those furrowed dolomites plot closer to the middle ground between the magnesium and calcite end members over here, and again expanded upon a little bit over there. So pretty contrasting chemistries between the barren rock carbonate minerals and the uranium-bearing calcite minerals. We can do the same exercise with the copper-related carbonates. Again, I'm going to highlight the major observations that I want you to take away from this. So in the case of the carbonates that are not associated with the ore, they end up plotting as more calcitic in nature. So again, coming from the top of that ternary diagram there. And then in the opposite case to what the uranium has, the carbonate minerals that are associated with copper mineralization are more dolomitic in nature, or more magnesium-rich. And as it turns out, these things are more distal to the ore body as well, so it makes sense that you might see something different away from the main ore body itself. And just to compare with what we were seeing in the previous slide, the range of uranium barren dolomite compositions actually turn out to plot slightly different in their iron and magnesium content compared to those that are associated with the copper. And then lastly, looking at the uranium-related calcite, they in turn plot slightly different from the calcites that are not associated with the copper mineralization at the Cashin mine. We can also look at the trace element geochemistry in this system, in particular the manganese and iron, given their potential for interpreting some of the redox state of the fluids that they were forming from. So on the y-axis here, we have the molar manganese content of these carbonate minerals. And on the x-axis, we have iron. So it's a little bit busy here, but I just want to highlight again the main takeaways. So high manganese to iron ratios are associated with the uranium ore calcite, and lower ratios of manganese to iron are associated with the calcite that's not associated with uranium. Again, the same exercise with the copper associated carbonates, where we have high manganese to iron ratios in those that are associated with copper, and lower in those that are not. Now, the reason that this is important is because with higher manganese to iron ratios, it's actually easier to get more manganese, or sorry, you assume that there's higher redox states to get more manganese into that crystal structure, and then it needs to be more reduced to have a higher iron content within them in order to get that iron 2+ in there. So it's not quite that simple, and I told you again that we'd see some more complexity exemplified with these images here. So it appears that with the calcites that are intergrown with those copper minerals, that there's a lot of oscillatory zoning that represents varying amounts of manganese and iron, where these bright zones represent high manganese to iron ratios, and the low or the dim zones representing lower manganese to iron ratios. And again, we can infer something about the redox state, where these bright zones represent high oxygen fugacity or more oxidized, and the darker areas representing a more reduced oxidation state. And that actually has implications for how we're interpreting ore formation to occur, because previous authors have interpreted these things as being a mixture between reduced and oxidized waters to actually precipitate copper in these environments, and ultimately that's reflected within this zonation in the cathodoluminescence of these calcites. So the last analytical method that I'll be showing today is looking at the stable isotopes within these different kinds of carbonates from the uranium and copper systems, particularly the oxygen within these calcites, which we can see here plotting in the orange and pink, where the orange represents the carbonates associated with copper, and the pink being those associated with uranium. It actually turns out there's actually quite a bit of overlap between those two, but they probably didn't form from the exact same waters, given the difference in the metals that they are. So what we can do is actually reconstruct these the equilibrium waters using knowledge about the temperature formation of these things, and we do that first with the copper-related carbonates, which, based on fluid inclusion analyses, we know to have formed roughly at 100 degrees C. So plotting it against this 100 degree C isotherm, we can then reconstruct it and see where it overlaps with modern day waters from the Paradox Basin region. And as it turns out, they look a lot like the connate waters or brines that are coming up from deep within the Paradox Formation, which is actually contains a lot of those salts that produce those salt walls within the region. We can do the same thing with the uranium-related carbonates. In this case, reconstructing them at 25 degrees C, which, as it turns out, makes them look a little bit more like the surface or shallow subsurface groundwaters that have been collected from the region. So again, this is an interesting way to actually pick these things out and separate them out from one another. So thanks for listening to all that. I'm just going to summarize these things really quickly with a few bullet points on how I've been able to study the Paradox Basin geology through the lens of ore deposits. So the different alteration features that we see, namely the addition of different kinds of minerals like carbonates and silicates and potentially even clays, vary in their spatial distribution based on the different kinds of deposits that we see. The geochemistry is complex, But by looking at the different compositionally distinct kinds of carbonates associated with these different metals, we can actually pick out different kinds of geochemical environments in which they formed, where we see differences in the manganese to iron ratios between ore-bearing and non-ore-bearing rocks. We can do something similar with the oxygen-stable isotopes to distinguish between the different fluid components that might have formed the carbonates and ultimately the different copper sulfides or uranium oxides within these systems. And then lastly, the new geochronology that I've shown you today is able to place different times of ore formation in the context of the Paradox Basin as it evolved through time. So with that, I'd like to thank you for coming, both in person and online, and open it up to any questions.
I have a microphone here. If anybody wants to ask a question, I will deliver it.
Thank you. A great talk, very interesting.
Thanks.
Hard to assimilate all of it, but I did have a couple of questions. One is the green clay smectite? That's one question. Another question is the light-colored sandstone adjacent to the red sandstone, does that actually have reduced iron in it that isn't oxidized?
Mm-hmm. So first question, there's a bunch of phengite in there, in those green mudstones.
Oh, is there? Okay.
Yeah, so it looks like the main difference based on some sort of preliminary EDS analyses of these red versus green clays is that there's sort of more iron 2+ within those green rocks as opposed to those that are found in the red rocks. And then the white sandstones contain a lot more pyrite than the pink and red sandstones.
So it's a reduced condition?
Yeah, exactly.
Okay. And then the ultimate source of the uranium, is that derived from like the Zoroaster granite or the 1.4 granites that were in the uplands that provided those streams that are coming down into the Paradox Basin?
Yeah, there's a lot of speculation surrounding that still to this day. I think people have been working on that question for like 100 years now. That's definitely a hypothesis that's been proposed. There are people that suggest that in the overlying brushy basin unit that sits right on top of the salt wash hosting all the uranium, that leaching of the sort of volcanic ash within those ancient lake beds could have been a source. There's also the possibility that sort of just these groundwaters having background uranium concentrations in them could have formed these ore deposits just with an efficient enough trap. So still out there. There's a lot of different ways to interpret this, but I'd like to sort of narrow them down with time as I'm working on my dissertation.
Do you think that the volcanism associated with the Morrison Formation was tapping into deeper rock that had uranium sources that were, say, pre-Paleozoic?
A lot of the ash is coming from the sort of the Jurassic arc, so that could be coming from things as deep as the slab as it's melting and subducting beneath North American continent.
Okay.
So there's a lot of things that it could have been passing through along the way up.
Okay, thank you. Oh,
Yeah.
well, one other thing, do you think that did the LaSalle's contribute anything in the way of either uranium or copper into the Lisbon Valley area?
Initially they thought that might be the source of uranium, but I don't think there was involvement of that. It's a little too far away from some of the deposits, given that they're all throughout the Colorado Plateau. With the copper, there's little copper deposits, but they're not sort of these sandstone-hosted things. They're sort of these copper lodes that we see just as you get sort of hot water churning around these magmatic phases.
Okay, two questions, but the first one has to do with the coffinite. And you have a lot of silica overgrowths there. And when you did the microprobe work, did you do quantitative work on it so you could work out the stoichiometry of the coffinite? And the reason I ask that is when you go through the literature, there's so much reference to coffinite, but when I've gone into various deposits and done microprobe work, there really hasn't been the silica there when you do real point source with the quantitative microprobe. So I was just wondering if you really feel certain if it's coffinite or because it's so fine grain and you've got 3 dimensions you're looking at there that you might not be picking up silica from the overgrowth.
Yeah. So those coffinites, if you will, that I showed are embedded within those calcite cements. So I'm confident that there's no silica that could be derived from a detrital grain or something else nearby. I mean, the volume that we're hitting is too small for that with the electron beam. But there's a distinct silica peak when I'm hitting it with the SEM. So
but there's no way to do any stoichiometry on it? You don't have quantitative work then?
I could if I brought it to the microprobe, but the focus with the microprobe has mostly been on the carbonate minerals.
Yeah. I just caution you to put more stuff in the literature about coffinite without documenting it.
Yeah.
And if there's some way you can do the quantitative work on it, it would be a really good thing to do. And
well, there's definitely silica. It's just the most obvious mineral to point to is coffinite in that case. And I'm sure there's other uranium silicates out there, but that was just sort of the more obvious thing to state.
And the second question has to do with the iron concretions. Have you done trace element quantitative analyses on the concretions? Because some of the stuff we found in the uranium deposits in Arizona have as much as 1,000 ppm silver in them, so they're kind of fascinating.
I have done it on those concretionary cements. I have not seen those levels of silver in it. I think that the main metals I'm looking at in there, sort of the more transition group metals like lead and zinc and even copper thrown in there as well. But I might have turned on the silver in that, and I don't think I saw anything above sort of detection limit with the machine that we're working on.
And I commend you, by the way, on being hesitant about the source of the uranium, because I know the questions Dan was asking you, and as you know, Ken Ludwig's uranium ages in Arizona go back as far as 260 million years, which puts it much earlier than any of the volcanic activity, the tuffs and the Chinle formations, much older than that. So.
Yeah, that's right. These complex systems that vary. Actually, so the question was about uranium in the Wingate. There is a weird little prospect I visited, again within the LaSalle district, and the Wingate is cross-cut by one of these sort of northwest-southeast salt wall parallel faults, and it's filled with uranium in the fractures. So my first thought on that is that there's probably a uranium deposit down below me somewhere in the hanging wall that's just been chopped in half and had fluids pumped through it and bringing it up into these fractures in the Wingate.
Do you think that the source of that was in the Chinle?
It could be if it's from the footwall, or it could be from Morrison Formation if it's in the hanging wall. It just depends on which way you think waters are moving up and down.